Hey there everyone! So today I would like to show you how to integrate some composite functions. Now notice that if I take the derivative of 1 over a exponential function to the power of ax plus b, what will I have? Well, a here and b are constants, so I can get a outside of that derivative. Now taking the derivative of an exponential function is the exponential function itself. However, I have to apply the chain rule since I've got some composite function up here. And when I apply the chain rule, I have to multiply by the derivative of the exponent, which in this case is a. Now, we should notice that we can cross those out. Therefore, my answer is the exponential e to the power of ax plus b. Therefore, the integral of e to the power of ax plus b dx is 1 over a e to the power of ax plus b. So let's compare with our e to the power of x, which is simply e to the power of x. Notice that now we do have 1 over a multiplying in front of it. Everything else is the same. What now if I take the derivative of 1 over a multiplied by n plus 1, which multiplies ax plus b to the power of n plus 1 close bracket. What would this be? Well, once again, a is a constant and a is also a constant, and b here inside is also a constant. So all of those here, I could just bring them out of our derivative. So a, which multiplies n plus 1. And now we have to multiply by the derivative of this second term here. However, when we take the derivative, this n plus 1 will drop. And not only that, this will be now less 1, so n plus 1 less 1 times ax plus b times to the power of n, because it was n plus 1 minus 1, so we cancel those out, and we can also cross n plus 1 out, so the derivative of that would be ax plus b to the power of n. So there we go, we've got another one of those composite functions integrated. So if we take the integral of ax plus b to the power of n, we should then get 1 over a times n plus 1 times ax plus b times n plus 1. That's another thing for another easy rule for us to apply and remember. Notice that even if you forget, you can still do all the working out. Now let's compare with our non-composite function. This would be integral of x to the power of n, and that would have been x to the power of n plus 1 over n plus 1. So once again, x here is replaced by ax plus b, and down here n plus 1, n plus 1. So the only change, once again, is the 1 over a. It's important to notice that in this case, n has to be different than 1. Otherwise, we would end up using the natural logarithm. Now, not surprisingly, if you take the integral of 1 over ax plus b dx, 1 over x would be the natural logarithm of the absolute value of x. In this case, if you had to guess, you would be right. It's going to be a 1 over a, and then the rest is the same, natural logarithm. Here instead of x, you will input your composite function. And obviously there will be a constant for all of those before. There will be a constant here, which I'm just not putting. A here has to be different than 0. Actually, in every single problem we've seen so far, a has to be different than 0. Otherwise, there would be no x, all derivatives would be 0. And also division by 0 is not very pretty. So if we apply the same concept to some trigonometric functions, so for example the cosine of ax plus b dx, guess what? 1 over a, and then sine ax plus b, and then plus c. There's a constant here again. Okay, in every single example, every single one of those examples, there will be a constant, even the ones that I showed before. Now what about sine? Sine of ax plus b dx, and negative, right, because sine and cosine, 1 over a cosine ax plus b plus c. And for those, a is different than 0 as well. A has to be different for any of the problems, any of the examples that I've just shown you. So a very quick example here, integral of 2x plus 3 to the power 4 dx. So, well, 1 over a here is 2, right? And then 2x plus 3, exponents plus 1, 5 over 5, plus a constant. So this is 1 over 10, 2x plus 5 to the power 5, plus 3 to the power 5, plus c. And that's it. So another example here, this time with a root and also in the denominator of a fraction. What you have to remember when you're working with roots is that a root of a number can be written as the exponent. So this, for example, is 1 over half. If you have, let's say, the nth root here, and this is to the power of m, that's x to the power of m over n. So you can always convert a root into an exponent and work with the exponent because you know how to work with those integrals and derivatives. So if we write this as integral of 1 minus 2x to the power of negative a half, because it's underneath, we should be able to work it out. Let me just fix this. There we go. So this should be equal to, and then again, we can just work like we did before. This is an exponent. It's going to drop, right? And in this case, since it's an integral, it's going to increase by 1. So if we take this, this is our exponent, and this is our a, negative 2. So 1 over a, 1 over negative 2. That's the first part, right? So integral of this, 1, negative 2. We increase the exponent by 1, so that's a half now. Negative a half plus 1 is a half over this new exponent, which is a half. plus a constant. So that should be negative a root of 1 minus 2x plus c. Just cross those out here. Negative is in front of everything, and the half I've rewritten as a square root again. Now please never ever bring this negative inside of the roots. That's not allowed. I've seen there more than I wanted to. Don't do that, please. That's not possible at all.